Hello and welcome to today's stream. Today I'll be looking at some Java language features, and specifically I'll be looking at generics. So I've done a session before on generics on one of Kenya Jag's episodes under Java for Everyone. Before I started streaming it live. I already did that, so I thought it would be nice if I did one for the stream, so that it can become part of the available library of sessions that you can go back to and learn about generics and other things. So under my channel, you can already find sessions related to the Java language, exploring a variety of features in the language. And generics will be just an addition to that. So today I'll attempt to cover all of generics, at least all of the generics concepts that I know when it comes to the Java language. And we'll talk about a bit of the history and some limitations of how generics is implemented in Java. But mainly I'll be trying to share what I know about generics and getting through some code samples, which should make it fun and interesting. So first of all, generics, when the Java language was first released, it didn't have generics. So Java 1.0, which I think was released around 1995. So this didn't have generics. So programmers or developers at the time had workarounds for writing quote-unquote generic programs without having generics in the language. And we'll try and look at some of the techniques that were used to address that weakness. And Java is not the only language that shipped without generics. So Golang as well shipped without generics, and generics was added later. So then in Java 5, I think in Java 5 is when generics was added. So generics was added to Java around Java 5, which was referred to as Java 1.5, I think. So that's when generics was added, and at this point, a lot of internal tooling and libraries were advanced in the language. So the way generics was added was not very convenient, and it led to some restrictions and some limitations in how far developers can take generics or rather utilize generics in the language. So during our exploration, we'll see some of those limitations and also look at how to bypass those limitations. If it's some of them are so inbuilt into the language that you can't bypass them. You just have to write your programs within the bounds and limitations of the capabilities of generics in Java. But with some of the limitations, there's some tooling and ways around it. But also there's a lot of capability in how generics is implemented in Java, so it's not just limitations. So to start this, we're going to have a simple class here, and the class is a box, and this box has the ability to store items. So the box can store integers, it can store strings. So for now, I'll have the box store strings, and the strings will be the element, so it can store an element. And I'll want these to be initialized with the constructor. So the way I do that is so the way I do that is by making it final, making it private and final. So making it private and final guarantees that we at least will be forced to initialize it in the constructor. and we pass in the value, and we'll use that value to initialize the element. So you can say this element is equals to value, so that will give us an initialization of that element. We can have a getter for retrieving the element, get element, which will return string. Okay, IntelliJ is already freezing up on me. This will be our getter, and its job will be to return the element. And we can have a setup for modifying the element, although we won't need it in this case, since we can just depend on the constructor. So that's our class. So I'm getting that error because I need to wrap it around something. So I'll just try and declare it within main. So you can have it here. So this is my class box. And we can use box by creating an instance of box. It's equals to new box, and initializing the element. So let's say this is hello world, and we can print the values in the box by calling box.getElement, and this will allow us to print out whichever value was added to the box. And you can see we get our hello world there. So this box, you can also use it to store numbers by making this integer, and that means we'll change this to integer, and this as well to integer. And now we can pass an integer. And you see we have 45 there. And I could use it to store double. Double, and of course this means we'll return double here, and now I'm storing 45.3, and if we run that, we'll be able to get 45.3. So there's already a limitation in that if I want to change the type, if I want to change the type of element, I have to modify box. But my use case requires me to be able to store multiple types of elements. So the way you can do that is we can say, since everything in Java inherits from object, we can say this element is anything that is an object. So I'll make this object, and here I'll return object as well. And now I can set this to 45. So let's say this is a doubles box. So it's a box that stores doubles. Doubles box. So I can have a doubles box that stores that double value. I can have a text box that stores a string like hello world. And if I print the value from that, text box dot get element, you can see that we're able to retrieve the element. And if I run this, you'll see we get a hello world, and we're able to print 45.32 as well. So this temporarily allows us to solve the problem of the box having the ability to store multiple types of elements. So we might find ourselves in another case where we might want to do some operation with the element that we retrieve from the box. So let's say I have this double here, and what I want to do is I want to get the square root of whichever value is retrieved from the box. So I can do that by calling math.power, and then I pass in the double value, get element. That will give me the element, and I can try and get the square root, and we'll print the square root here, square root. So I'm already seeing that we have problems because a get element is an object. So, and math.power only works with doubles. So you can see from the documentation, we are supposed to pass in a double, which is the value and then the power that we raise it to. So this is square root, so it's 2, 2.0. We could also use just 2D. And this would work unless we cast the value, because what we want is a double. The value that we want to use for that square root function. In fact, this is square, not square root. So the value that we want to use for the square function has to be a double. So when we call a doubles box dot get element, we expect this result to be a double, and you can see it's not because it's object. So the way we solve for that is we can cast it to a double. So I can cast it to a double like that and pass that double value to our power function. And now we'll have value that raised to power 2, and we're able to get our square. So if we execute that, we see that now we have, let me have a simpler value that, so let's say this is 2, so let's say we are passing in 2. So if we pass in 2 as the value of the element, so that's an integer, could use that 2D to make it double. And now we're able to see that we have 4. We can print this a little bit better. So what we have is the value that we passed in, which is double box dot get element, and we are raising that to we are raising that to to 2, and the result is the square. So if I run that, you can see, so we are getting the square. This is not the square root. The square of that value, which is 2 raised to power 2, and that gives us 4. So this works. I'm able to do that operation with that. But if I try to do the same thing with this text box, so if I try to get the value from this text box, let's call this value 2, and we call the text box dot get element, and since we know this is object, we attempt to cast it to double. You notice something, the compiler is not able to detect that this cast cannot work because the text box stores strings. It doesn't store doubles or integers or numbers. It doesn't store a number that we can use. And in this case, we are looking for double. And although we are doing incorrect casting here, the compiler is not able to detect this for us at compile time. So we'll run into problems when we try to use this value. So let's go ahead and try and use it. I'll call this square 2. And if we call math.power, and we take value 2 raised to 2D, yep. So if we take that value and raise it to power 2D, then we try and print the outcome. In this case, I'll use the same printout as the one we used here. So you can see at compile time, all of this seems to be correct. It almost seems like nothing can go wrong. So if I go ahead and run it, because now what I expect is I will cast it to double, and then we'll raise it to a power by passing in the value of double. Of course, the power function accepts this because we are casting to double, and we raise it to power 2. So let's see what happens. So we see we run into a class cast exception, and that is because we cannot cast this to double. That's referring to that line. So we cannot cast this to double. There's no problem with that. The only problem is that this is not detected at compile time, and we only run into it at runtime, which is rather inconvenient because when you write programs, you expect that if there are any type system related issues that you probably got incorrectly, the compiler should be able to detect them and let you know, so that you don't ship a piece of code expecting everything to work, and then when it gets to the customer, it starts to crash at runtime. So that's why compile time checking is important. So how do we prevent this from happening? So let's imagine I only have this case, and what we want is to fix for this problem so that we never run into this, and have the compiler work for us, have a compile time detection of this problem. So the way we can do it is we can start to utilize generics. And what generics allows you to do is you can define a parameterized type. So a parameterized type is defined using these brackets, and you pass in a symbol in between. And you can define the parameterized type at the class declaration level, like this. And that means we can allow this box class to have a generic type. It can have member variables that conform to the parameterized type. So like in our example, the element can be a parameterized type, and you can use T to represent that. And when we do that, now whichever parameterized type will be used during the initialization of instantiation of this box class will end up being utilized for any operation within the box class. So the way you define that parameterized type is at the instantiation level, you use the same style of brackets, and then you pass in the type that you want to be your parameterized type. So now this instance of box will only work with doubles. If you wanted one dedicated to text, so let's say you want one dedicated to, let's say one dedicated to integers. So integers box is equals to new box, and we can change the parameterized type like so, and this will work with so this is integers, so you can change the parameterized type to integer, and this will work with integers. So you can have 3 there, or 45, whichever integer value you want to pass in. So since we've specified this works with doubles, you'll see that at compile time we are getting the error there that is telling us that this needs to be a double because we've specified the parameterized type to be double. So we can only pass a double value here. We can't even pass integers. So something like 32.32 would work, 32.11, that would work, but any other type would be rejected. The IntelliJ does too much sometimes. Makes me want to move to Vim. So this one, so this is a double box, and now when we do casting, we're able to do casting correctly, and typecasting, can do typecasting correctly here. In fact, we might not even need to do typecasting because we've already specified the type, and if we run it, we're able to avoid that runtime exception. So let's say I made the same mistake we made earlier, and this was a text box. and I've specified that it's the parameterized type is double, and I'm trying to parameterized type. So already we are not able to pass in a string here. Well, let's assume we overlook that. So when we call this and try to do a cast, so if we try and do a cast to double, of course, since this piece of part of the code is already broken, we won't get to even doing the cast. So we already saved from that that issue, and yeah, so that helps us with that. So it will be very unlikely for you to find yourself doing this. So if we are not initializing this with the with the constructor, perhaps we have a no argument constructor here, and since this is final, I might need to initialize it to something, maybe null. So that allows me to skip passing the value, and now I'm doing a cast. So if this was a string and I attempt to do a cast, you'll see that we get a compile time check for the type, because we've specified that this is string. We can't again cast the element to double. The restriction applies. Yeah. So that's how you use the parameterized type to limit the bounds of your generic class. So that leads us to the next part of generics, which is bounded generics. So what we're using here right now, this is unbounded. This is unbounded generics, in that this type can be anything. It can be string, it can be integer, like we saw. So if I was working with strings here, this would still work fine, and we'll be able to use string. And if we were just printing the value, I'll just print the value. So we'll be able to print the value. Of course, here the value will be null because I didn't initialize the value. But we can utilize the setter that we defined to set the element. Do we have a setter? No. So we can define a setter here, and this will set the element, and the type is, of course, we're still using the parameterized type t, and you can use that parameterized type to initialize the element. Okay. Yeah, I made it final, so I think that's why I'm having problems there. Yeah, so if I'm going to change it later, with the setter function, it can't be final. Yeah, so but anyway, we can now call the setter and set the message. The message here is hello world, and if we run that, we'll see that we get our hello world message. So now the box can work with any type. It can even work with custom types. So I could create another class, call it shape. And so this is a class that stores shapes, and it has 1 or 2 arguments. Let's say it has X and it has Y. And of course, I could use some setters for this, but I'll use final, that we're able to initialize them at the constructor level. So public shape, and I can pass in X and I can pass in Y here. This dot X is equals to X, and this dot Y is equals to Y. And we can have a box that that is able to store shapes. So shapes box is equals to new box, and this is a box that stores shapes. And when I call shapes box dot set element, I can set in a new shape and pass in the x and y like so. And our shape can have a toString function, and this toString just prints the coordinates. So x is x, and y is y. And we can print the value we obtain from the box by calling get element. And now if we run it, we should see that we get our x3 and our y2. So essentially the box can work with anything. So in some cases we might want to limit the bounds of this box. So you can have various types of shapes. So perhaps we have a shape that is a rectangle. So you can have a rectangle, and we can say that this rectangle extends a shape. You can have a square that extends shape. And of course, if we do that, we need to handle the constructors. I didn't import anything weird. Okay. So you can have the constructors for that's what you can call super on shape and pass in the x and the y. And here you can have int x and int y. So you can have square, and in fact, let's do something, have something more interesting. Let's have a circle, and a circle can have the xy, but also you can have radius. So you can have the radius as a variable for this. Let's use double radius, and you can have the constructor for the circle, double radius. I'll use r for the radius, and int x and int y. And we can call super, passing the x and the y, but also initialize the radius. So these are qualifying shapes. So what if you wanted our box to only work with shapes? So we don't want it to work with any other type. The reason why we might want it to only work with shapes is if we were utilizing a particular operation that's available to shapes. For instance, a function that calculates volume, for example, or a function that prints coordinates. So let's have a function here that prints the coordinates, show coordinates. And what that does is it just prints the current coordinates. X is x and y is y. So that's a specialized operation that's only available to shapes. And any class that extends shape will have access to this operation, and no other class will be able to have access to that operation. So if we wanted to do that kind of operation within box, perhaps when initializing the box, we want to print the coordinates here. say current coordinates. And we call value dot print coordinates. So basically calling this function show coordinates. So as you can see, we can't use this function unless value can imply the ability to work with shapes. So let's try and limit the bounds of this type to shapes that we're able to access some of the capability that's defined in shape. So the way you define bounded types is at the point where you're declaring the parameterized argument, the parameterized type, you use this extends keyword. There's a cases where you use super as well, but in this case we'll use extends. And we'll say as long as t extends shape, not that shape, the other shape, class shape. Okay. Looks like we can't see it. So my code can't see it. Well, it's there. Let me declare it externally. It's a different file. Class shape, and we'll just move this to that file. And hopefully able to see it. Package generics. Okay, so this is where the freedom that comes with Java compact files reaches its limitation. So it looks like there's a limit on the number of inner classes I can define here. Okay, so we're able to detect that shape. So this is the shape that we're using. So let's see if we can go on. So you can use the extends keyword to define the bounds. So once you use that extends keyword, this parameterized type T will be limited to only classes that extend from shape. So classes like rectangle, like circle, will qualify as values that can be used here. And now you'll notice that now I can call value.show coordinates, which is a function defined in shape, this function. So despite this being a parameterized type, I'm able to access that show coordinates function. Yeah, and now if I try to instantiate a shape and say that this will store integers, you'll see I'll have an error saying that integer is not within bounds. So this is only limited to classes that extend shape. So if I used circle, yeah, that would work. And now when setting the element, I can set it to the circle, and the circle I can pass the radius. Perhaps the radius is 1.5. 1.5, coordinates is 3 and 5. So I'm able to successfully create a box that's able to store shapes. So and this is a circles box, so this can store circles, and we know that circles extends from shape. So yeah, you can see that being a capability. So maybe you can define a custom toString function for this, and we have 3 fields. So radius, So we can print the radius. We can also print the x coordinate, x, and we can print the y coordinate, y. So since they're not instance variables for this class, it might be tricky to access them. I don't know if I can use super here. Oh yeah, so we can nest this with super.toString to get the string representation of our super class. We can create some space and we can call super.toString, and this should call this toString function for the shape class. So it will call this and then append the values that we get to the radius value. So if we print that, we should see something. So radius is 1.5, and then we have x is 3 and y is 5. So this is an example of bounded generics. Within the Java language, there are interesting other examples. For instance, if we can limit this to number. So if you wanted to do, you want this box to be limited to only number types like double, integer, and you want, because you want to do arithmetic operations like the power function or addition or multiplication, you can say that a t must extend number, and the number is an abstract class within Java that every number type extends from. So integer, you'll find that integer extends number, double extends number, and so on. So if we went to integer, java.util.integer, okay, can't find it there. Perhaps that's it. So you'll see that this class integer extends number. It would be the same case with double. So if we went to double, you'll see that double extends number. So if you define the bounds of this box to number, it means it can work with doubles, it can work with integers, it can work with floats, and multiple other types. So let's see an example of that. So I'll get rid of the circle example, and let's try and work with numbers this time. So this extends number, and let's see what we can gain from that. I think with that I can probably simplify this a bit more, since we are not relying on any other external class. Perhaps we can go back to a more simple format. Okay, so we just have the box, and our box has those properties. But now, since we know that we've restricted it to number, we can add some arithmetic operations here. Like we could do square root, and after the square root, we get a double. Sorry, square. Keep confusing that. Square, let me call it SQ, and with this you just pass in the power, so like 2, 3, whichever power you want to raise it to, and this element will be raised to that power. And the way we can do that is we can call math.power, and we can use the element and raise it to that power. So you'll see I'm having a bit of trouble here. So despite limiting this to number, I still need to make it a double, because It could be an integer, it can be a double, it can be a float. The only thing we've restricted is that it has to extend number, and there's multiple classes that extend a number. So since we are extending from number, there's some utility functions available in number that we can use for this. There's long value, there's float value, there's double value. So we can use those to cast whatever value we have, and this is how you do it. You can refer to the element and obtain the double value. Since there's a guarantee that any class that extends number will implement these abstract functions, so you're guaranteed of getting the double equivalent from a float, double equivalent from an integer, or double equivalent from an actual double. So whichever number that's passed in will have an implementation of this abstract class there. So if we go to integer and we look for double value, you'll see there's an implementation here. So if we're passing an integer to the box, this will be what we'll be relying on to convert the integer into double. The same way, if you went to the double class and look for double value, you'll find that it just returns the current value. So that's how that works. So then, so since we're able to obtain the double value here, I'll call this the value, and we can use that value on the square root function. We could extend this and do multiplication. Let's say we are doing integer multiplication, and we want to multiply to that different value. So I'll call this target value. We want to multiply it with something, and we can return this dot element times target value. Target, yeah. So the same way we'll face some problems because we're not able to ascertain what kind of number this is. But since it's within the bounds of number, we know within number we have this int value that's available to us, this function, and what we can do is just refer to it, int value, and that will give us the int value, so that our multiplication function will be able to function. So you can do this with many other arithmetic operations, and we're only able to do this because we've defined the bounds of the parameterized type. So let's do an example. So I'm going to create a floats box. So this is a box that can keep floats. And in the float box, I'll set the element to that float. Let me use like 100 float. And because it's this box, it means I can call these functions, the square root and multiplication functions. So I can call square root and square, whichever that with raise it to power 2, of course, to get the square root. In fact, since it's square, we don't even need to pass this value, so you know it will always be 2. To be safe, make sure it's double, so we don't need to pass in that second value, and we can print the result of that operation. Square equals to that. We can do multiplication the same way. So this is multiplication of with the float box dot multiply, and we are multiplying it by some value. Let's say multiply it by 5. So multiply by 5. So that's 100 multiplied by 5. So let's see those operations. So let's see, its square root, of course, will be that number multiplied by 5, which is 100 multiplied by 5, you get 500. So limiting the bounds of this parameterized type means despite our element being generic, we're able to perform more or less specialized operations. And you can do this with your own custom classes, and or you could also do it with inbuilt language level inheritance, like number and the classes that implement that extend from number, that is double, integer, and the other boxed numbers. Yeah, so that is bounded generics. Let's see if we can look at something else. So far we've been looking at generics at the method as at the class level. That is, the parameterized type is defined at the class level. It would be interesting if we can have generics at the method level. So like this set element can be generic on its own, get element can be generic on its own. And the way we can do that is we can have a static function. So let's say we had a static function, and the purpose of this static function is to perform subtraction. And what after the subtraction operation, we expect, let's say it's doing integer subtraction. So at the end of that operation, subtraction, at the end of that operation, we expect an integer, but it's a static function. Being a static function means it doesn't have access to this parameterized type, or rather that parameterized type doesn't make sense for static functions. So if I was to pass in t here and call this first value, you see that t is not recognized because box.this cannot be referenced from a static context. Basically, you cannot reference the parameterized type t in a static context. But let's imagine I still wanted this function to be generic, and I wanted it to have the same bounded generics that we're using here. So the way you do that is before the return type, I believe it's before the return type, you can specify the parameterized type. So I'll use e for this. You can use any symbol, and I'll say that e extends from number, and e extends from number, and now my first value is e, or we could call this first element. So at the method level, I'm able to define a generic type e and use it in the function. So since I've specified the bounds work the same way as if you would declare them at the class level. So there's not a restriction there. And with that, I can do some operation. I can take the first element, get the int value, and add it to second element. Since this is static, I'm not able to access element because that's an instance variable. So let me make these first and second. So second dot int value, of course first and dot int value. We're able to get subtraction. So this is subtraction here. So first and second. And with that, we can call the static function. So let's say we are subtracting 100 from subtracting 150. So we can call box, and since this is static, we won't be using float box. It's a static call dot subtract. and we can pass in any number here. We could pass in maybe 13.34. We can pass in an integer. So we can even pass in different types as the first and second argument, as long as they extend from number. So for example, you can pass hello world here because that's a string. So you can still pass 5. Yeah. So if we have something like 1.25 plus 1, and this is 1.25, sorry, minus, it's subtraction, minus 1. And we can see what happens with that. So 1.25 minus 1, and that should be the value. Did I return the value? Yeah, should be able to print it. Yeah, so it's 0. You can do maybe 10.43 minus 9. Sorry, maybe 5.6. And we have 10.43 minus 5 point. In fact, I want this to be integer, so I'll keep it 5. And we'll see we get a 5 there. And the reason why we're getting 5, of course, is because we are returning an integer explicitly. So some restriction, while experimenting with this, I noticed it could get tricky if you want to return E, despite defining the bounds. You are kind of limited. Let's see, perhaps it's possible. Let's see if we return integer instead of. But I'm also already doing casting, which is usually a bad sign. So even when we do casting, we still don't get the desired result. Let's see if I do it correctly. Yeah, so we're still not able to get the desired result, which is, so this requires E, although integer falls in the bounds of number, we are not able to return the integer. So this goes back to the limitations I was talking about at the beginning. So you'd expect that since we've defined E as the parameterized type and we've specified that it's any value that extends number and integer extends number, so then I should be able to use it as a return type and able to return the integer, and perhaps even that would allow us to return any type, but unfortunately that's not possible. So this could be related to a small matter of type erasure in the language. So what type erasure means is at compile time, you can have this fancy declaration of the parameters type E extends number. You can have the unbounded T like we had at the beginning. But at runtime, when the JVM is executing your code, everything is converted back to an object. So like in our case, this argument where we're passing E.first, this would just be a regular number. And since it's a number, this operation will still work, succeed at runtime. So the parameterized types, the parameterized type arguments like E and T are essentially erased at runtime, and they're replaced with either object or their superclass equivalent. Yeah. So that could be related to why, that would explain why we are not able to return E. Or it could probably be related to some other issue. But anytime I face those restrictions with generics, I always assume it's something related to type erasure. So at runtime, it won't be able to deduce the return type that I was expecting there. So if I wanted to return number, perhaps that would still work. But the caller must explicitly be expecting a number. But also, if I'm returning number, then I'm explicitly casting that to the super type. While writing the code, it would be nicer to just use E. Yeah, so that is generics at the method level. So you can use it like that. So you just specify the parameterized type. If it's bounded, you can specify the bounds. This doesn't always have to be bounded, so it can be any type depending on how you have designed your function, and depending on your actual logic within your function. So in some cases, this might actually work. You might just be able to process any type, and we'll see examples of that, especially when working with the collections. When you're working with collections, you don't worry that much about the type of value that's passed to your collection, and that allows you to utilize unbounded generics more. But when you are writing stitched code like we are, where you're doing something very specific, using bounded generics really helps, because you can bring those specialized operations to either your method level definition or your class class instance methods, and it allows you to pack in more capability within your functions. So let's look at another concept. The concept we'll be looking at is the idea of wildcards. So wildcards in Java are represented with this question mark symbol. And what essentially the wildcard means is, so it's usually represented like this. What essentially this means is where it's declared, you're essentially telling the caller that you can handle any type. So it's a form of unbounded generics, but bounded generics in terms of the instance method of the bounds. So you can think of this as where you are using, you're passing an instance of a class that supports parameterized arguments, but you want the parameterized arguments to be of any type. So I think the best way to explain this is through an example. So let's say we have a static function. If I can just declare it here. So if we have a static function, if I should, let me get rid of that so that we get some more space. So we have a static function here that does something with boxes. So we know boxes have an element as an argument. So let's say we have a function that prints that element, but it's a static function, which means it's declared outside of the box itself. So static void print box elements. And what it does is it accepts a box as an argument. And okay, can I still use it here? It looks like I can't use it here. Perhaps outside the function. Okay. I'll try using it outside the function. Okay, so we have that, but now it can't see box. Let me get the box outside the function as well. Maybe then it can see it. Okay. Yeah. So we have this static function. I'll make it public, and it can accept a box, and it can print the elements of the box. So box element is box dot element. I don't think it's good accessing it like that. Let me use the getter. And I also made it private, so it's interesting that I can still reference it. But anyway, what I'm doing is I'm passing the box as an argument, and I'm just printing the element. And here I don't really know what will happen because the element can be any type and I've not defined the bounds of that type. So let's see what happens. I'll move the main function below that so that we're able to use it. And here I'll just call print box elements and I'll pass it a box. So let's have a box and this is a box of strings like a text box goes to new box, and it's a box that can handle strings. Are we talking about the same box here? Or I changed it so that we don't have to pass the value, but also this should work. Text box is equals to new box, and then we specify the parameterized type. Oh yeah, so we still have the bounds checking here. So I'll get rid of some of these functions. Get rid of this some of these functions, and we make the box unbounded, so it's t of anything. Yeah, so that should allow us to use string, and I can call text box. So I'll pass the text box to the print function. So let's see what happens in this case. So box element is null. Yeah, of course we haven't passed in any value, so I think I can pass that value at the constructor level. Hello message. Yeah, so box element is hello message, so it's able to print the value. So that's all good. You can print most types. So it can, if I have int box, that's a box that can store integers, and it has 3. I can call print box and passing the int box, and we are able to print 3, the value 3. The other one we're able to print the value hello message. But if my static function is doing something a bit more specialized, like if I'm doing an arithmetic operation, perhaps I'm doing an addition, and it's an integer addition, so if I'm doing integer addition here, and I'm adding whichever value is in the box to another number. So to make this make more sense, okay, I'll expand it a bit more later, but right now I'll just pass in a second integer. Let's call this int b. Can use that, and what we'll do is we'll take the box, retrieve the element, and then add it to int b. So you can see already we have a problem here because we are not able to ascertain that the element can actually be used in an arithmetic operation, such as addition in this case. So what that means is we might need to specialize this static function a bit more. And the way you can do that, one option is you can go to box and add the bounds. You can add the bounds to the box here. Say this only handles number. And that would solve your problem slightly, in that now you can call int value, and this would work. But if this was perhaps an internal API or some library that we're not able to access and go and edit, you might not be able to go in and change the signature of the parameterized type. So what do you do? So in our case, we can go ahead and specialize. So you see, if I remove the bounds, we are not able to call int value. So we can go ahead and specialize this static function a bit more. And the way we can do that is we can say this box, we can work with any box, a box of any type. Remember the wildcard. You can work with a box of any type as long as that type extends number. So if that type extends number, they can be used as an argument. And you'll see once I do that, I think we should, so I was hoping to get some compile time checking for this, that because this is string, should be able to pass that in. But anyway, so we're able to limit it to a box that has a parameterized type that extends number. And what that means is we can go ahead and call int value. So we're able to access that int value function. Oh yeah, this is the print function, so it's not affected. So what that means is if we now call the addition function, which is a static function, and we pass in an int box, since this int box is limited to integers, that can work, and then we can pass in the second integer, like 50 maybe. So that will be okay. Let's see if we pass in a text box and pass in the value that we're supposed to add. So you'll see there's a compile time error, and it's telling us that the expected bounds for whichever box we pass to this static function must be in the bounds of a class that extends number. But this is a string. String doesn't extend number, so this will be illegal, and it will be detected at compile time, which is the biggest benefit of working with that. And now we can just have the addition function, and this will do the addition operation. And we know that without changing box, you see box is still unbounded, our static function is able to work within very specific bounds, because the nature of the operation we're doing in that function requires that the parameterized type of box is actually a number. So addition result is, so it will be the value of that addition operation. So if we run this, we'll see that we get 53. That is 50 added to 3. And you can have another static function that also does, let's say this time we have a static function that only does string operations, like concatenation. So this will return a string, and what it does is it will append the string. Let's say it's a function called append str, and the bounds is we're only working with text here. So if a value is a string or it extends from string, I think this is where things will get a bit interesting, and that will be a box, and we are appending the next string. If I'm right, we'll probably need to do some adjustment before that works, or even if it works as is, we'll use that to explore some other concept. So let's return whichever element is in the box, and so you can see I'm able to access a string function like concat and next string. So since this is bounded to string, I'm able to access concat. Concat is a function that's available in string.java, so I would not be able to access it otherwise. So if this was a number, I would not be able to access string. If it was shape, the shape we defined earlier, which for some reason I'm not able to access here. So if it's a WT shape, I'm not able to access. We will not be able to access that concat function. So this has to be string. And now if we do a concatenation, let's say we have our text box, which is this. See if I can move it lower, move it a bit closer to where our print function will be. So the print function is hello, and let's say I want to append in whatever values in the box, I want to append world, like that. So this, after the end of this, we'll get another string, which means I can print it in line. And that will form our message. So if we run that, I will see we have hello world. So it's hello, then you concat world, and you get that. So you can see that we're able to define those bounds. So you can also use this kind of representation for the bounds while defining the bounds when you're working with the wildcards. But I've not been able to understand clearly the difference between that and extents. Because let's say we use it here for number. So as if say super integer, let's see what happens. Yeah, so I still don't understand how this works particularly, specifically. So I've always used extents, but you can also use super if you understand the difference between representing super and using extents. That is something related to inheritance hierarchies. So there's one that works where you limit it to your subclasses, and there's one that works where you limit it to superclasses. So if I used super here, I'll not be able to access the concat function. But if I used it, I think even with the number, if I use super, so this erases that operation. And yeah, maybe I can try and look it up and see how that works. But we've learned the core and critical parts of generic. So this is now on the edges of generic. So there's this, and then there's intersection types that are a bit hard to understand. So the difference between super and extends with the wildcards in Java. So somebody asked, what is the difference between super and extends in Java generics? Classic Stack Overflow, it was okay, it was a duplicate. Java, this is also a duplicate. Anyway, this is why people stopped using Stack Overflow. So the wildcard declaration of list extends number means that any of these are legal assignments. So number, integer, double. Yeah. What about super? List, that, super, that. The wildcard declaration of list, super, integer, foo means that any of these are legal assignments. Okay. So I guess that means if we use super here, yeah. So if we use super and this is integer, that should make the box value integer. doesn't seem to be the case. Still have these strange imports. Cannot be applied to capture super java.lang.string int. Okay, so it's still not clear. I'll be honest, this is the bit of generics that I still don't get. Perhaps because extends is much easier to interpret in terms of inheritance hierarchies, because when you say whichever value extends from number, you know that any class whose super type is number will qualify. But with super, it's still not clear. Perhaps because I'm used to thinking of inheritance hierarchies from top to bottom. So perhaps super works in reverse from the class that already extends from it to a number. So you're moving from integer to number, not number to integer, perhaps. But even that, the examples I've tried out, it has not worked out. It does not produce the desired result. Yeah, something to explore if that's something you're interested in. But extends already meets most of our requirements. I believe there's some edge case where you might want to use super, but it's still not clear. If it's something that you understand, you can type on the chat and let me know. Yeah, thanks, Prasan, for watching. Yeah, so that is that. Let's see what. So we discussed type erasure a bit. So what I explained with type erasure is at runtime, this will be, so all these parameterized arguments will be replaced with either object or the superclass representation, like number in our case, or shape, where we were using shape, and using that to instantiate instances where one of the instances contained rectangle and circle, and both rectangle and circle extend from shape. So at runtime, all your rectangles and your circles will be converted to shape type. Yeah, so we've covered all of generics. So now maybe we can close this by looking at how you can use generics with collections. So I'll just do a simple example where we are using, I think we can do an arrays example that's not really collections framework, more like fundamental data structures of Java and any other language. So let's see. Let's use an array and then we use a list with this generics and see how it works. We could, since this is a box, it should be capable of storing more than one element. So I'll rename it to elements. To kind of define its new responsibility. And these elements will be an array. And because it's an array, it's safe to initialize it early. So it's an array of type T elements. And since it's final, so if it's not initialized here, we can initialize it as an empty array. Why can't that work? Why can't I make it? was hoping to make this an empty array. Okay, I think cannot be instantiated directly because it's a parameterized argument. Okay, I'll just make sure that the array is initialized properly. And we can do that by passing the array of values that we'll use to initialize it there. And this setter will become irrelevant since we're working with an array. Arrays are they are not, so in this case it will be a static array, it's not dynamic. So we can't, once box is instantiated correctly, we won't be able to change the size or the elements of the array. We can change the individual elements, but we cannot change the size. And here we'll be returning an array. So that's our new box. So our box is able to store elements, and our get element function will now be get elements. So I'll get rid of some of this, all of these static functions, and let's use this with an array this time. So now that is T, it means we can have an array of any type. So it can be an array of integers, an array of strings. So I'll create an array of integers for a start. So I'll create an int array is equals to new int, and I think just pass in the values. So that will be our int array, and we can create a box. So this is an int box. It's equals to new box, and this, the type will be limited to integer, and can pass in the array. The other thing, I think this is very important and I forgot to mention it. Generics doesn't work with primitive types. So in Java we have object types and we have primitive types. So object types are like integer, like doubles, like float, and the primitive types for this would be int, you have double, you have float. So these act as wrappers to the primitive types. And the main difference is in terms of memory layout. So this will store a pointer to where the actual double is stored. This will store a pointer to where the actual int is stored, but this one's mapped directly to memory. So when you're working with generics, this would work with generics. This would pass. So this will work with generics, but these other ones won't. So this works with generics. Object types, you can use them with generics. Primitive types you cannot use with generics. So important to remember. So because of that difference, this will be integer instead of int, and we should be good. And what I'll do is I'll just print the array, int array, and hopefully I won't need to do extra work to print it. Okay, so I'll have to do some extra work to print it. So we can look through and print the elements one by one. I don't know if there's a shortcut to this. Oh yeah. I was printing the entire box. Let's see if the elements will be printed. Okay, so still not able to. Let's see. yeah, we'll have to do some extra work for this. So the way we can print the array is we can use a for loop, which IntelliJ is already writing for me, but I'd like to write that. So int I is equals to 0. So this should bring memories of C. Check the length, I plus plus. And now with that, we should be able to print the array. So get elements and print the element at that index. Yeah, so we have our 3, 3, 4, which is the values we have here. Maybe I can extend it a bit. 3, 3, 3, 4, 5. So so you can see you can use generics with arrays. You can declare an array that stores quote unquote generic elements, or rather utilizes the parameterized argument as the type of elements that will be stored in the array. So the same way we can use arrays, we can also use lists. So you can have a list here, and this list accepts elements of type T. And this is a bit absurd for me to write, because a list by definition actually does that. It's generic. But let's, for sake of argument, let's use it with box, and then we'll use it without box, just to demonstrate that you don't need to do that. And our argument now will be list of type T, and of course a list of type T here. Where this can be useful is you can use it to limit the elements that are stored in the list. So you can say only work with numbers. So it means this list will only be able to work with numbers, at least within the context of the box, which it's something we should experiment with. So let me leave it open for now for the example, and then we'll change it up and see what happens. So same case, in fact, we'll utilize some of this code. So I'll create a list here. Let me be very explicit about it. So we have a list of integers. Int list is equals to new array list. And I can pass in some values to that. Can pass in 4, 1, 2, 2, 3, and we can pass that int list as argument to our box, and we can print the elements in the box. So with the list, the toString or the print function is provided for you out of the box. So if we call int box dot get elements, we should be able to see the elements. So you'll see 1, 2, 3. So that's done for you, which means if we could go to this and say just return these dot elements, and in the context of a printout. I think even if I did that, it would still get the hint. And if I print the box here, should still be able to get the desired effect here. So you can still get 1, 2, 3, because it will call toString, and then toString will reference the list, and then list will provide the toString, the internal toString function, which prints the elements like this. So let's try to limit the bounds. So you can only work with things that extend number, and instead of int, we have string here, and it has hello, it has world, and it has exclamation. And rename it to just list. And we pass in that list, and this now is a string. So you see we have some problems. So if this was still unbounded like that, I think would still be okay. So if we run it without the bounds, we'll see we'll get hello world with exclamation. But if we limit this parameterized type to number, we are not able to use string. So so you can use this to make sure that your list only works with particular types. So that's one way you can improve your list. That I can imagine this would be used for some optimization thing. If you know the exact type of the elements that are available in your list, and the caller is not able to surprise you with a different type, despite your class being generic, you might do some additional optimization work, or you might do some basic functionality related work. So let's say we want to generate the sum of all the elements and return the int representation of that. Sum all elements. Come on, elements. Because we know all of these are limited to numbers, what we can do is we can get you can iterate them. So you can say for int element in elements, integer element. Okay, so since they are numbers, okay, we can still use t there. We can convert them later. So for every element in elements, and that is that list, we want to make a sum. So sum is 0. And to sum these, we can just say sum plus equals element dot int value. So since the bounds is int, and then at the end we just return the sum. And if we did that this time with actual integers, let me get rid of that. So I'm back, but I'm not sure whether my stream is still on. So I got interrupted there for a bit. So I'm just trying to make sure everything still works. Everything seems okay. I just want to be absolutely sure. Okay, so we got disrupted a bit, but we'll resume from where I left it off. Although I'm sort of in the dark here, I don't know whether the stream is still on or it got disrupted completely. I'm seeing indication that it might be a different stream. So I'm not very sure. So what I'll do is I'll stop it where I left it, and then on a different stream, we'll be able to explore collections a bit more and see how that goes. But at least we're able to cover generics the previous stream exhaustively. So what's left is just looking at collections. Yeah, my stream got interrupted, so too bad. But we're able to cover plenty. So I'll see you guys on the next one. Like and subscribe.